Imagine working hard on a state-of-the-art chip design, only for it to fail before production. No signs, no warnings, just a silent killer at work. A tiny spark you don't even feel can destroy your entire circuits. That's electrostatic discharge, ESD, a major threat to IC reliability. Many designers overlook it until it's too late. ESD failures are costly, unpredictable, and can lead to mass recalls. The worst part? You may never see the damage until it's in the hands of the customer. But ESD isn't random. It's predictable and preventable. Every IC you design is at risk. If not properly protected, even small voltage surge can cause cumulative damage over time. We must integrate ESD protection from the very beginning of the design process. Ignoring ESD can lead to product failures that damage a company's reputation. ESD-induced failures can range from immediate device destruction to long-term reliability issues. With proper design techniques, we can ensure that our chips withstand these unpredictable discharges. Today, we'll cover why ESD matters, what it is, and how to design for it. By the end, you'll see how small design choice can prevent big failures. But first, why do we even need ESD protection? Picture a chip fresh from fabrication, perfectly functional. A worker pick it up, and in a fraction of a second, it's dead. A simple touch can generate thousands of volts of static electricity. Manufacturing, handling, and even normal use introduce ESD risks. Have you ever walked across a carbon and feel a shock when touching a doorknob? That's the same principle at work. But while you barely feel it, your chip is far more sensitive. The damage caused by ESD is often invisible and happens in microseconds. Chips may pass initial tests but degrade over time due to the undetected ESD damage. Failures in the field can result in massive financial losses and frustrate customers. In semiconductor manufacturing, ESD can cause low yield and production delays. Even automotive machines generate static charge that must be accounted for. ESD failures lead to customer dissatisfaction and damage to brand reputation. Industries such as aerospace, automotive, and medical devices require high reliability and must mitigate ESD risk. This is why global standards exist to ensure IC meet minimal ESD requirements. ESD protection isn't just an option safeguard, it's a necessity. But what exactly is ESD and how does it cause so much damage? Great. ESD is a sudden flow of electricity between objects with different charges. It happens when electrons jump quickly to balance voltage differences, like the mini lightning strike. This charge imbalance can occur naturally and be induced by external factors. When someone touches a chip, charges redistributed rapidly, leading to high voltage surges in ICs. Even a few hundred volts can destroy transistors. Human bodies can generate thousands of volts just by walking. ESD events can occur from simple interactions like plugging in a cable or handling PCB, ESD doesn't always cause immediate failure. Sometimes it weakens devices over time. Gate oxide breakdown and junction failures are common results of ESD. Once damaged, a chip might appear functional but have a reduced lifespan. Manufacturers simulate ESD events in testing, but real-world conditions can be unpredictable. The semiconductor industry uses multiple models to classify ESD threats. Understanding this risk is crucial to designing robust ESD protection. ESD damage is often cumulative, making it difficult to detect until failure occurs. We can control and redirect this energy to protect circuits. How do we design circuits to survive ESD events? Yes, ESD protection is about controlling where the energy goes. Instead of damaging sensitive circuits, we redirect it safely. We use diode, resistors, clamps, and layout techniques to protect a low impedance path to the surge to dissipate. Think of it like a lightning rod for your circuit. It takes the heat, so your design doesn't. ESD style helps safely discharge excess energy away from the critical components. Power clamps act as a high-speed switches that limits voltage spike. Resistance in series can slow down discharge paths, protecting delicate nodes. Grounding techniques can play a role in reducing ESD risks. Even PCB materials choice affect how well a circuit can dissipate ESD. Shading and enclosure design contribute to overall system-level protection. Proper routing ensures that protection elements achieved before the IC is exposed. High-speed design requires careful optimization of ESD structures to avoid signal degradation. The challenge is designing protection that works without compromising performance. A well-designed ESD protection network is inevitable until it's needed. Without it, your chip is left vulnerable to sudden, irreparable failures. Incorporating ESD safeguards from the early design phases ensures robustness. An effective ESD strategy balances protection and performance for reliable circuits. Let's break down key ESD protection components. The core of the ESD protection is diodes and clamps. Diodes act like a voltage-dependent switches, absorbing ESD spikes. They are strategically placed near sensitive input and power rails. Resistors limit current and control discharge paths, preventing uncontrolled surges. Power clamps create a low resistance path to display high energy passes. These elements work together to ensure the chip stays within the safe operation voltages. Different applications require different protection strategies. Rail-to-rail protection is common for digital circuits, while analog designs need customized approaches. Pad-to-ground structures help in low-power applications, where linkage is a concern. Internal protection ensures sensitive transistors are not exposed to high voltage. Layout plays a critical role. Poor placement can make good protection ineffective. Parasitic effects can degrade performance, so careful design is necessary. Understanding how different protection elements interact is a key to a robust ESD design. Different circuits need different ESD architectures. Rail-to-rail, pad-to-ground, and internal protection Now, let's look at the real-world ESD design challenges. Designing for ESD protection comes with challenges. One major issue is balance protection and performance. High-speed circuits are particularly sensitive to additional capacitance from ESD structures. If protection elements are too aggressive, they can degrade signal integrity. Conversely, weak protection leaves the circuit vulnerable to damage. Finding the right trade-off is critical. Circuit simulation helps predict how ESD structures impact performance. Placement is another challenge. Poor routing may make protection ineffective. ESD current must flow along the control path to avoid unintended damage. Advanced packaging techniques also influence ESD robustness. Some designs require custom ESD solutions tailored to specific applications. Understanding the impact of manufacturing variations is also crucial. ESD protection effectiveness can change due to process shifts. Designing with reliability in mind ensures long-term product performance. Next, we explore how to test and verify ESD robustness. Testing and verification are essential to ensure ESD robustness. Industry standards define specific test methods for evaluating IC susceptibility. The most common tests are human body model (HBM), machine model (MM), and charge device model (CDM). Each simulates different real-world ESD threats. HBM mimics a person touching the device. MM represents ESD from handling machinery. CDM replicates charge accumulated on the device itself. These tests involve controlled voltage paths applied to the IC. Engineers measure it if the device survives without degradation. Failure analysis techniques help identify weak points. Scanning electron microscope reveals microscopic damage caused by ESD. Lab tests guide iterative improvement in production design. Verification isn't just about passing the test. It ensures field reliability. Simulation tools complement physical tests for deeper insights. Robust verification helps avoid costly product recalls. With verified design, IC can meet industry standards and customer expectations. Global industry standards dedicate minimum ESD protection levels. The JEDEC and IEC standards define test methodologies and pass criteria. JEDEC JES 22A114 governs HBM testing. JESD 22C101 outlines CDM invocations. Automotive IC must comply with IEC Q100, which has strict ESD requirements. Customer electronics follows IEC 61042 for system-level ESD protection. Compliance is essential for marketing acceptance. ESD failure rate must be within acceptable limits to ensure reliability. Different industries impose varying levels of ESD resilience. Medical devices damage extreme reliability due to life-critical applications. Military and aerospace IC must withstand harsh environments. Designing to meet or exceed these standards ensures long-term robustness. Meeting standards isn't just a formality. It guarantees a product's real-world visibility Understanding compliance requires early prevent costly redesign. The next step is to apply ESD knowledge to practical circuit design. What happens if we ignore ESD protection? Without it, failures are inevitable. Even if a chip seems to work initially, latent damage may appear later. Early product failures lead to massive financial losses. Recall can cost company millions and damage reputations. Imagine a smartphone that suddenly stops working due to the ESD event. Customer trust errors and impacting failure sales. Manufacturing yield suffers if chips fail during the production. PCB failures in assembly systems cause debugging nightmares. High reliability industry like automotive cannot afford sudden failures. Fail returns due to ESD are expensive to diagnose and repair. Negative ESD protection can turn a great design into a costly reliability. Implementing proper safeguard is a small effort compared to the potential losses. A well-designed circuit ensures customer certification and long-term success. Let's conclude with the key takeaway and action items. Here are summarized images showing you why ESD is an inevitable but preventable failure mechanism. Proper protection ensures product reliability and longevity. Key strategies including using dial, clamps, and proper layout techniques. Understanding industry standards help avoid compliance issues. Early stage simulation reduce late stage design failures. Testing and verification validates robustness before production. Ignoring ESD protection leads to field failures and financial losses. Good ESD design balances protection without harming performance. Engineers must continually update design as technique evolves. Every high-speed circuit requires customized ESD solutions. Think about your designs. Are they ESD safe? Start reviewing your circuit now. Implement ESD protection early to avoid costly failures. Stay ahead by keeping ESD-based practices in mind. Let's make reliability a priority in every design. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.